Hi, everyone. Welcome to the fourth lecture of our online series, Scientifically Speaking. I hope I'm audible. This is an hour of fun knowledge sharing and interaction with a world expert, and it's designed just for you. So I hope you enjoy it. I'm Ritu. I'm a second year student at Ashoka University, and I'm majoring in computer science. Majoring in CS at Ashoka has been a really interesting journey for me, especially because right from my first year, I got to experience research through something called ISMs, Independent Study Modules. And the exciting part is not only did I get to conduct research with experts in computer science, but also with experts in biology, and I got to interact with professors doing neuroscience. And so this interdisciplinary approach to research has been really interesting and fantastic, especially because real life itself is interdisciplinary. Another fun thing at Ashoka is that I play the Indian musical instrument, the veena, which is right here. And because it's such a big, heavy instrument to transport, Ashoka bought a veena for the university just to encourage veena players. So it's a really interesting, enriching, encouraging atmosphere to grow up in. So our aim with this Scientifically Speaking series is to introduce you to cutting edge research and innovative teaching techniques. We have a new topic and expert every week, and we go on a journey together to explore subject through the perspective of data and science. Before I introduce our speaker for today, Professor Ravi Kotari, let me just go over a few logistics. I'll be interviewing the professor for about 30 minutes today, after which you can ask questions using Zoom's Q&A feature. You can do this either with your real name or you can send in your questions anonymously. That's up to you. And don't worry if you miss out on any part of this lecture or if you want to rewatch it because we'll be distributing this on YouTube and other platforms. Also, stick around for the end of the lecture because we're going to have a quiz and the top 5 winners are going to get really exciting prizes. So stick around for that. So let me introduce Professor Ravi Kotari now. He is a professor of computer science, and he's the head of the department here at Ashoka. Previously, he was the director of the Artificial Neural Systems Laboratory, and he also received IBM's highest award for his achievements as an individual and for his team. So that's really impressive. Let's talk to the man himself and find out more. Professor Kotari, welcome to the Scientifically Speaking series today.
Thanks, Ritu. Thanks, and hello, everyone.
So, Professor, you have so many impressive achievements and awards, but like take us back. Tell us when you were a student, what got you interested in computer science, and what similarities or differences do you see between CS at the high school level and CS at our university or research level?
So, I was always fascinated with how we learn. So, you could look at a small child, and the child learns how to walk, falls many a times, but then starts wobbling, and then eventually starts to learn. There's an immense amount of motor control that has to be choreographed for us to walk. I mean, we take it for granted, but it is a very complex exercise. We learn to recognize objects, which is again very complex. And I was always fascinated, how is this child learning? I continue to be fascinated, and that was the first sort of my affair with machines and machine learning.
Wow. So, can you tell us a little bit about your research right now and your expertise, your field of expertise?
So, my field of expertise is in machine learning. And I started with machine learning. I was fortunate enough to sort of stay with the same field, even though I applied it to different things. But it is primarily machine learning. And more recently, it has become things like creative machines. Can we have machines which can create new things? And also has started venturing into the ethics and the policy of machine learning.
Yeah, all hot topics and buzzwords we're reading in today's news. I feel like we're all really excited. We can't wait to start building our own self-driving cars. So I'm handing it over to you, Professor.
Thank you, Ritu. And hello, everyone. I hope I'm audible and you can share. You can see my screen. Uh, Let me start. I'm sure many of you or most of you have heard of some of the spectacular things that machines have achieved recently. For example, you might have heard of machines or cars that drive themselves. You might have heard of machines that have beaten chess grandmasters or beaten the world champion at the game of Go. Lots of very impressive feats. And you might be wondering, how exactly is this machine doing that? So what we want to do today is to take a journey. We'll start at the beginning, and we don't want to assume anything. So we'll start at the beginning, and we'll take a journey into intelligent machines, and we'll then go to the next frontier, which is towards creative machines. So I hope all of you are excited and to join me on this journey. So this is the sort of roadmap we'll follow. I'll first start with the classical approach to AI. This is something that existed perhaps 30 years ago, but it's nonetheless still very instructive. We'll then take a more contemporary look at how we create intelligent machines today. I'll then take you into an application that you've heard a lot about, self-driving cars. And I assure you that by the time we reach this part, you will feel that you can create one of these. We then go on to the next frontier, which is our first steps towards creativity. And I'll finally conclude with a very serious application, something that is very, very useful, and that is designing new drugs or new cures in some sense. Okay, so this is the classical approach to AI. We'll illustrate it using an example. So on the left is a chessboard. You're all familiar with it. There are two players, white and black. Each player has 16 pieces, and the board is a 64 square board, and white usually plays first. Now, the game of chess, when you start out with, white essentially can move any of 10 pieces. So white can move any of the 8 pawns and can move either of the 2 knights that are there. So this is represented in the classical approach in terms of a tree. So what you see on the right is a tree. The root of the tree is the starting point. Level 1 of the tree corresponds to the different plays that white can make. So the first child of the root node could be moving the leftmost pawn. The rightmost child may be moving one of the knights, and so on and so forth. So it corresponds to a possible move that white can make. You could go down one more level, and those correspond to all the moves that black can make in response to a white move. And you can imagine that you can build a tree, perhaps very large, a large number of nodes, but nonetheless, you could create a tree. And then the game of chess simply becomes, if you find yourself at a given point, at a given node, you choose the path which is most likely to lead you to a win. And it becomes a matter of enumerating this tree and a matter of searching this tree in a very clever and a very efficient fashion. So this classical approach to AI generally relied on enumeration and then very efficient search through all the options to find something that is the best, that gives the best rewards. As you imagine, the number of options are very, very large. And so this classical approach to AI runs into problems very quickly. With a game of 64 squares, the total number of options are actually more than the total number of atoms in the universe. So you can imagine that if you took a more complex problem like driving a car, the number of options would be very large. So we come to this more contemporary approach to AI, and this is not unlike how we as human beings try to solve a problem. So to illustrate this, consider a very simple problem, optical character recognition. So the post office might employ optical character recognition because people address envelopes by hand, and the post office wants an optical character recognition system that can scan, automatically figure out the destination, and sort the mail accordingly. So we are going to take the core part of this OCR problem, and the core part of it is trying to recognize a handwritten character. So what you see on the left is an example of a handwritten character. And the idea is not to search through all the possibilities. Keep in mind that not everybody writes P in the same way. So in the classical approach to AI, you would have enumerated all possibilities, and then you would have recognized the 26 alphabets. But in this particular approach, in the more contemporary approach, you take this picture, so to speak, and you transcribe this picture into a vector as shown. So in this vector, perhaps 0 corresponds to a white square, 1 corresponds to a black square, and you move from left to right and top to bottom. So this is a grid of 6 by 5. So you end up with a 30-element vector. These 30 elements go into some machine. I've depicted a neural network, but it could be some machine. And the machine outputs what the character is in that particular grid, in this case, a P. For me to show you how this works, let's take a slightly simpler example, and then I'll come back to this optical character recognition problem. So this slightly simpler example is, imagine a conveyor belt, and this is a very realistic industrial application. I mean, there might be things coming on the conveyor belt which needs to be sorted. But since this is a simple example, we are going to imagine that what comes on the conveyor belt are apples and oranges. And there is a camera, there's a field of view of the camera as shown, and the output of the camera goes into a machine. And the machine has the task of deciding if what is in the field of view is an apple or an orange. If you look at the diagram below the conveyor belt, the machine might decide that it is going to find out the color and the sphericity of the object in the field of view. So you're shown color and sphericity in the bottom figure. And this machine, this neural network that we talked about, in this particular case is a single neuron. A neural network is a connection of neurons, but in this case, I just want to illustrate what a single neuron does. So the two inputs, color and sphericity, go into this neuron through coefficients W1 and W2. There is also a coefficient W0, which has an input which is always fixed at 1. Now, a single neuron synthesizes or realizes an equation which is given below. Y is a function of W0. Notice that W0 had an input of 1, so it's W0 times 1, plus W1 times color, which is represented by C, plus W2 times sphericity. So this equation is what a single neuron realizes. Now, if you look at the argument of the function, we can rearrange the terms of this so that S is equal to minus W1 over W2 times C minus W0 over W2. This is the equation that you see in the rightmost figure. Now, obviously, as I change W0, W1, and W2, this line, this is the equation of a line. It's sort of like Y is equal to mx plus C. M, the slope is minus W1 by W2. The intercept is minus W0 over W2. So as I change the weights or the coefficients, this line is going to change in orientation in this plane. And the idea is that I want to take a lot of examples, examples in which I know the input and I know the corresponding output. And I want to adapt, I want to change the coefficients, I want to change the weights such that there is a line which best separates the apples from the oranges. If I'm able to synthesize this, then when I get a new piece of fruit on the conveyor belt, all I need to do is to pass it through this, find out if the argument is greater than 0, in which case it's on the right of the line. If it is less than 0, it's to the left of the line. And if it is equal to 0, it is on the line, and we could flip a coin and decide if it's an apple or an orange. Okay, so you would also realize that W0 has an important role. W0 essentially controls the intercept of this line. And if W0 was not there, then the line would always pass through the origin. So to have that flexibility, we want W0 to be present.
So, Professor,
Yeah.
You mentioned, may I ask, you mentioned that W0 in this graph was set to 1. But suppose we change that number or we multiply it by some other number, what would happen?
It won't make a difference, because if I multiply the whole equation by something, or I could divide the whole equation by something, it would still correspond to an intercept. It's still a constant of some type. But essentially, the role of W0 and that input is to control the intercept. Okay, so let's go back to the OCR problem that we had. Now that we understand what a single neuron does, let's see how we could use that to classify handwritten characters. And we have generalized it, made the problem slightly more complex. So instead of zeros and ones, since pens are not homogeneous, they release different amounts of inks at different points, or there could be smudging on the envelope on which the handwriting appears. We could have percentages of squares of that grid which have ink in them, and some part of it which doesn't have ink in them. So we could encode it such that the numbers correspond to the percentage area that has ink in it. So we could recode this whole thing as a vector, which is now a vector of real numbers, still a vector of length 30, or you could keep it as still 0 and 1 as we had before. And this could go into a neural network, again, a single neuron, and perhaps the single neuron, we could establish this line, this sort of a decision boundary. And on one side of the line could be all the P's, and on the other side of the line could be all the other alphabets other than a P. So P might be an apple, everything else is an orange. So you imagine that the single neuron is able to produce this differentiation. Of course, to the left of the line, there might be many, many P's corresponding to the different ways people write a P. We want to take this concept a little further. So if you see on the top part, we have now extended that single neuron to 2 neurons. And we still have 2 inputs, color and sphericity. Both the inputs go into both the neurons. Now, the top neuron, neuron 1, the top neuron would synthesize or would realize a line, would realize an equation, and that line may be this blue line in the right plot. Neuron 2, or the bottom neuron, synthesizes another line, and that neuron could be this green line in this plot. Now, we have added this third neuron. And this third neuron has the benefit of seeing the output of neuron 1 and 2. And it can say that, well, I'm going to output a 1 where there is an intersection, where neuron 1 says to the right of the line and neuron 2 says to the left of the line. So essentially, this magenta neuron can now say I'm to the right of this green line and to the left of this blue line. In other words, it's referring to this wedge-shaped region that is out here. And it can say that everything in the wedge-shaped region is a P, everything outside the wedge-shaped region is not a P. My point is that you could come up with more complex decision regions than simply half planes or one side of the line. We can, of course, extend it to more than 2 inputs, and shown below, the machine might have decided that I'm going to come up with 3 inputs as opposed to 2 from the image. And now the neurons have 3 inputs. Obviously, the output of the neuron is now a function of those three variables: color, smoothness, and sphericity. So if you plot it, it's going to be a plane in a three-dimensional, in three dimensions. So neuron 1 is going to synthesize the blue plane in three dimensions, and neuron 2 will synthesize the brownish plane in three dimensions, and the magenta neuron is now going to find intersections or unions or combinations of the regions formed by these two neurons. So you can imagine that if we now go back to the optical character recognition problem, I may not have a single neuron, but rather I might have a neural network. There are many, many neurons, and there may be 26 outputs. And output 1 differentiates between P and everything else. Output 2 differentiates between Q and everything else, and so on and so forth. And each of these neurons each of these output neurons now, the one responsible for saying this is a P or this is a Q, tries to find combinations of hyperplanes that were realized by neurons in the previous layer. So given this, you can obviously see how to build a sophisticated neural network, how to make it do this optical character recognition problem. But let me broaden the aperture a little bit more. And let's say we wanted to do a self-driving car. Well, as before, let's say we have a camera mounted on the hood of the car or on the dashboard. And it may not be a single camera. It might be multiple cameras. It might be cameras, ultrasonic sensors, etc., etc. We'll just refer to it as a single camera for brevity. So there is an image that the camera acquires. This image goes into a machine, and the machine has to decide what to do. It can decide to brake, it can decide to accelerate, to steer left, to steer right, to brake while steering left, and so on. And the machine can also identify the objects that are in the field of view. So for example, car or a truck, not unlike identifying an apple or an orange. If you look at the plot on the right-hand side of this slide, you see that now the regions are more complex because the number of inputs that the machine computes from the image could go into thousands. So instead of it being in 3 dimensions or in 2 dimensions, you now have a 1,000-dimension space in which you're forming these complex partitions. And a partition is the union or the intersection of the things that were established by the previous layer. And these complex partitions correspond to a brake or an acceleration or things of that nature.
Professor,
And yeah, Rutu, please go ahead.
may I ask, what does the black line on this graph correspond to?
Yes, so that is a great question. So the black line, the neurons synthesize not just boundaries or not just decision regions or not just partitions that are bounded by lines, but if you introduced more layers into the network, you could actually synthesize boundaries or decision regions that are bounded by curved surfaces as opposed to lines. So the black line is depicting that the partition may be of an arbitrary shape. Okay, so now I want to take you down this, take you further into this journey, and we want to now see, can machines create? So shown on the screen at this point is a neural network. There are some number of inputs which are depicted by the neurons in yellowish brown. There are outputs which are depicted by green. The number of outputs are equal to the number of inputs. And the middle part of it has magenta colored neurons. This is what we often also call as the hidden layer. So the inputs represented by X go into the network. They get compressed into fewer neurons, the magenta colored ones. So the input gets represented by few neurons. And those few neurons, that representation is then decoded to give you Y, or the output, Now, the encoding part is the part from the input to the magenta neurons, to the hidden layer representations, to this latent space. And the decoding part is from this latent space, from this hidden representation to the output. And we want to train this such that X is always equal to Y. Now, I might have, for example, thousands and thousands, perhaps millions of faces. So X and each face might be 1,000 by 1,000 pixels. So X may be 100,000 in components. The vector X might have 100,000 components. And what I want is that these 100,000 components get represented in perhaps, let's say, 1,000 in their neurons. And those 1,000 then get decoded to give me back 100,000 outputs, which represent a picture, which is what was the input. Obviously, you will realize that the hidden layer tries to abstract the most salient characteristics of the input. It is only in that case that it can fully reconstruct the output. Now, at some point, once my network is trained, I can throw away the encoding part, and I could pump in artificial or synthetic inputs into the magenta neurons and ask those inputs to be decoded and get an output. If I do that, I'm not guaranteed that what I'll get as output is a face, because what I'm feeding into the magenta neurons is not something that comes from true faces, but is something that I'm randomly generating, and I don't know what the decoding of those random inputs is going to be. So we need to make a small change before we can start realizing creative machines. And this small change takes this form. So in the diagram, the left part corresponds to the encoder that we have seen before. But rather than directly producing a hidden layer representation, what we have done is we want to produce something, some set of parameters that approximate the distribution that is produced or that would have been produced at the hidden layer. So that those parameters represent, or those parameters give us an idea as to what the distribution was. Now, you might recall distributions from your probability class, but just a quick refresher. Shown at the bottom is a Gaussian distribution or a normal distribution, which is fully characterized by two variables, the mean of that distribution, which is where the center of it is, and the width of the distribution, which is characterized by the standard deviation. So you could have a more complex distribution, in which case you might need more parameters to fully characterize it. But nonetheless, this Gaussian distribution will serve a purpose. So this is a Gaussian in one dimension. I could, of course, have a multinomial distribution or a Gaussian in many, many dimensions. So what I want the encoder, the layer after the encoder to do is to estimate the parameters of the distribution that characterizes the output of the encoder. From this distribution, I'm going to sample a point in very high dimension space. And that sampled point is what I'm going to pass through the decoder to get back my output. Notice now that if I throw away the encoder part, I could keep generating samples from something which is a high fidelity distribution to the representation of the latent space. So the sample that is generated has statistical fidelity to that latent space. And therefore, any sample I produce will likely result in a Y that corresponds to faces if X had corresponded to faces. And this is what is a generative model, because I'm now going to generate many, many samples, not all of which I've seen before. And those new samples are going to produce new outputs. So let me give you some interesting examples. So on the left is an image of a person. On the right is an image of another person. Everything that you see in the GIF in between, or in the morphing set of images in between, are actually synthesized by samples from that distribution. So the first image, the image on the left was seen by the network, the image on the right was seen by the network, and once that those parameters were estimated, now you're sampling from that distribution. You're perhaps tweaking that sample. You might introduce things, and some introduction might correspond to a mustache. Some other types of tweak might correspond to hair, and so on and so forth. So you could play around with that sample so that you generate outputs which are of specific type now, or which have specific characteristics. Now, I've left a lot of the complexity aside, but in concept, this is what we can do, and this is amazing. I mean, we are now synthesizing faces, right? It's almost like an artist could synthesize new types of paintings if I had in fact trained the network with paintings. To give you an example, this is a portrait or this is a painting that was synthesized by what we have just discussed. So it was synthesized purely by a machine. And it was in fact auctioned at Christie's, and somebody paid more than $400,000 for this machine generated portrait. But nonetheless, you could also reflect on the fact that this portrait might look or might pass as an original painting by an established artist. So you can imagine that now the machine is getting more and more creative. And I want to just extend this a little bit further and show you that it's not just, of course, we could have generated music if I had in fact trained it with music. I could have trained it so the image on the left that you had, instead of that, it could have been Western classical music or Western jazz. The image on the right could have been Indian classical music. And I could synthesize fusion of those two, which corresponds to what is happening in between. But let me show you a more sophisticated example. And perhaps this example is relevant to the times we find ourselves in. And this has to do with drug design, is designing new molecules, designing new chemical structures. And shown in the diagram is a chemical structure. There is a language we have, which is called SMILES, which allows us to represent that molecule as a string. So once we are able to represent that molecule as a string, I now have the same generative model that we have discussed before. The input is no longer an image, but the input is the string, the SMILES encoding of that molecule. The output is also a SMILES output, and in fact, it is the same string that I feed in as input. I could, of course, look at databases such as Zinc, in which there are many, many chemical structures and their properties that are stored. I could train this structure, this generative model that I have, based on the entire set of examples that exist in the Zinc database. Once I have trained, I could remove the encoder part. I could sample from that distribution that we mentioned, and each sample could go through the decoder and give me a new molecular structure or give me a new chemical. I could, of course, have something following that in the pipeline, and that follow-up thing could evaluate the likelihood that the realized chemical structure has a certain type of property. So I could close loop this entire thing, generate, structures in real time, evaluate if they're likely to have some properties, and come up with a subset of structures that are very, very likely to contain something which I am looking for. I could, of course, be looking for something that binds to a particular type of receptor. I could be looking for something that has a certain toxicity profile, and so on and so forth. In fact, one of the most potent antibiotics was actually discovered using a scheme very similar to this one. This antibiotic was discovered a few months ago at MIT, and it's something called Halcin, and it is one of the most potent antibiotics that we know today, and discovered very rapidly purely through this structure. We have gone through a lot of things. We started with, with the classical approach. We went to a more contemporary approach. We looked at intelligent machines, and now we can generate art as well as new drugs. And at this point, I'm very delighted and I'm very proud to introduce somebody who was a student at Ashoka. He graduated in 2019, Kaushik Verma. Kaushik was also in my advanced machine learning class. And as I understand, Kaushik has gone on to use a lot of the things he learned in that class and thereafter to do some interesting things. So I'd like to invite Kaushik. I'm very proud to invite Kaushik to tell us a little bit about what did he do at Ashoka, what has he done since that, and what is it that we see on the screen at this point in time. So, hi Kaushik.
Hello, Professor. Thank you so much for having me here. So, after graduating from Ashoka, I've been working as a new media artist in the domain of art and artificial intelligence, right? So, most of my artworks are primarily neural network generated, and what you're looking at on the screen is one of them as well. So, on the left is this image generated by a neural network that is trained on a data set of botanical images, right? These are botanical paintings that contain paintings of flowers, of bouquets, and flower pots and stuff. And so, what the machine is trying to do is generalize on the distribution of these paintings and try to extract patterns from these images, right? So the objective of this neural network is to produce an image such that it is different from all the flowers and all the images of paintings that it has seen before, but it still carries the traces of what it means to be a flower, what it means to have that particular texture that was there in that painting. So if you look at the image on the left, you can't at any point isolate like, okay, yeah, that particular component, I can say that this is the start and the beginning, this is the start and that is the end of a flower, right? So it kind of combines all these different textures that it has seen in this data set in very creative ways and like outputs this as the image that we're seeing, right? And what's fascinating is to see that such an image is actually produced by a machine. And like whenever you see machines that are exhibiting a creative potential like this, it's really hard to believe because we ourselves associate creativity as this unique set of abilities to humans, and it's kind of odd to see when you have a machine that seems to exhibit the same creative qualities as you are, right? So we always think like whether it's writing poetry or composing music or making a painting, all these things are something that we kind of like associate very close to us or something that we define ourselves by. Like what it means to be human is to engage in these creative practices. But here you have machines that are doing these things too. So what that tension creates is place for a conversation where you have questions on what it means to be a machine in the first place, and more than that, what it means to be human in the first place. If the distinction between these two entities are becoming blurred, if the abilities between these two entities are becoming blurred, what does it mean to be either of them, right? So these are the kind of questions that I myself ask in my artworks, and the kind of process that pushed me is primarily because of the kind of experience I had at Ashoka. And like that's what led me to make most of these artworks that you're seeing here.
Thanks so much, Kaushik. I should
Yeah.
also mention that Kaushik was a computer science major at Ashoka, and he graduated in 2019. Okay. Okay, so that is in a nutshell and very quickly. I hope you have some idea of what machine learning is all about. And more importantly, I think you are closer to this ultimate frontier that we are now trying to explore. And that is machines that not only do things very efficiently, but machines that can actually be creative. Thank you, and I hope you enjoyed listening.
Thank you so much, Professor. That was really interesting. I feel like We all learned a lot, especially a new way to think even about creativity and machines and drug design in this time, especially. We've got a poll up so the audience can choose from the options we have for the poll. Um, so make sure you choose wisely and choose fast. And Professor will be answering what the poll answer is. Professor, what do you think most people are going to choose?
Uh, well, I might say, I mean, all of these are very good answers. I don't think there are any bad answers that I see. all look very good to me.
So we have so much new knowledge about AI right now, but Professor, I think the question that we really have now is how do you know where to apply this knowledge? How do you identify a problem that can be solved with AI or that could use AI?
Yeah, so that is a very, very good question, Rutu. I mean, something that we should pay a lot of attention to. There are some problems whose solutions we know in closed form. So, if, for example, I asked you, something about a pendulum. Now, you know exactly, equations of, physics-derived equations that tell you about how the pendulum is going to behave. So if you know something in closed form, you don't want to use machine learning. There's no point in applying machine learning to something whose solution is known from first principles. It is also a fact that the number of things that we know in first principles is very, very small, probably less than 1%. For example, if I asked you, how do you ride a bike? Write me the equations that govern your riding a bike. Now it has become very complex. Or if I asked you, how do you ride a bike which only has one tire? Now it has become even more complex. And so if you are faced with a problem which you do not know how to solve in first principles, that is an ideal machine learning problem. But if you know the first principles, by all means, you should use those. You should use that first.
Thank you. That was a very illuminating answer. I didn't think of it that way.
So
I
looks
think we
like
have the
the
poll
audience.
results. People thought, yeah, I mean, most people thought it would be a brain, and the next highest answer was robot with free will. What do you say, Professor? What's the answer?
The answer is actually a lookup table. So in order to explain the answer, uh, imagine that so a lookup table is essentially an infinite lookup table is essentially something which has infinite memory, right? It is, think of it like a diary of yours, which has infinite number of pages, and you have the ability to record every single thing that is going on at every moment of your life. Now, if there is such a lookup table, then essentially it has captured everything that has happened. And so when you encounter something, all you have to do is go into the lookup table and forget the part about very clever indexing and searching and all of that. But in concept, you could go into this lookup table, find out what happened at that time when that thing had occurred prior to this, and use that answer. So a lookup table is a very, very powerful concept. And specifically, if you had infinite resources, then you could construct an infinite lookup table and this basically, record every single event that ever happened.
Wow. Oh, we're getting so many audience questions. Let's try to answer some of them. There's so many questions and not much time, so I'll try to get to as many as I can. And apologies in advance if I pronounce any names wrong. I'll try my best. The first question is from Harshit Chabra. How can we say that thinking and creativity for a computer is the same as it is for human, given that computers operate on different principles, like bits and circuits, than us humans who use neurons?
So the synthesis of creativity might follow different paths, but that does not mean that the end result is different. Right? Of course, these are very early days. I mean, it's very hard to define creativity, even though we have been doing it for a long time. So the way to achieving it might be very different, but the effect of it might be similar.
So the next question is from an anonymous attendee. When AI is finally introduced, what kind of influence will morality have in their working? Will it follow something like Asimov's three laws? I love this. I love Asimov.
I'm sorry, Rutu, the audio broke up in between. Could you repeat the question, please?
Oh, yeah, of course. Our anonymous attendee asks, when AI is finally introduced, what kind of influence will morality have in its working, and will it follow something like Asimov's three laws of robotics?
Uh, so that is a very interesting question. Obviously, as machines start becoming more capable, uh, there are many questions that come up. Questions that obviously machines are trained on data. So, and data could have various restrictions on it. There could be private data and things of that nature. So the ethical issues around machines are obviously there. There are regulatory issues around the use of data. So machine learning has to contend with that. And there are obviously policy issues that surround data. So for example, if you build a self-driving car and the car goes and hits something, does the insurance cover? Right? And we don't have, we haven't evolved all of these processes to that point. So obviously lots of things would have to change, and they would have to be governed in much the same way that internet is governed to some extent today. Right? I mean, at the point the internet was introduced, there were similar type of questions. So these are obviously very good questions, and that requires a collaboration between computer scientists, between philosophers, between policymakers, between government, between various parties, and that's what makes it so interesting.
Our next question is from Chitra Desai. Is W0 a parameter or a hyperparameter? Let us know what exactly is a hyperparameter.
W0 is a parameter. It has its function or its role is the same as W1 or W2. The special characteristic is that rather than a variable being input, what goes through W0 is a constant, is +1. So it's a parameter like any other trainable, tunable parameter in the network. It's often called the biasing parameter.
And a hyperparameter? Like what exactly is that, the function?
So a hyperparameter is a parameter that depends on other parameters. Right? So in many situations, you might have things that depend on other things. So for example, uh, there are various things that we did not consider, the type of activation function, the function that was there, which is also called the activation function. It could have several parameters of its own. And those might be hyperparameters because they're parameters within parameters.
Deepro Chakraborty asks, does encryption use the same principle as generative models?
No, because a generative model is not supposed to come back necessarily with the exact same thing as a human. If I feed in something which if I feed in the latent space that originated from a true input, then the output that results may not be exactly equal to the input. On the other hand, when you encrypt something, everything is deterministic. There is no loss involved in the encryption or the decryption process. So the two are different in that sense.
Wow, these are really great questions from our audience.
Yeah.
Rohan M asks, since our inputs are discrete, how does the encoder obtain a continuous variation that is a Gaussian distribution?
The inputs are not discrete, as I said in the follow-up OCR example, as you saw, there was a fraction of the square in the grid that had ink, and therefore the input was 0.25 or some real number. So the 0, 1 was just to make it make it simpler to convey in this very short amount of time. But the inputs could be not just real; they could in fact be complex.
Wow. Atray that asks, recently an image has gotten popular, which is a mix of objects, but none of the objects can be identified. In the way the telltale characteristics of a flower were studied and recreated in the painting, like Kaushik, how can objects be studied to create an image that does not show the characteristics of any particular object?
Okay, so I think we need to clarify the image that Kaushik showed has elements of the images that were used to train. It's just that you cannot pinpoint that this came exactly from this image. It had a blend of all of those images. And the blend was to the extent that now you could not associate the output with one or a few images. So you could have multiple objects and you could synthesize something which had characteristics of these objects. So for example, there might be an object like a ball which had a bouncy characteristic. There might be something else which had vertices, which had edges instead of it being round. So you might synthesize something that has vertices, that has facets, and is also bouncy. So it has elements of both of them. And obviously, this is an example with just two objects. If there were thousands and thousands of objects, you could synthesize things from a subset of those. So it has characteristics. It has some small degree of overlap with each one of them, but perhaps not to the extent that you could say that this is an object of this type. Now, it could, for example, if you wanted to generate faces, you would say that this is a face. I mean, this is an image of type face. Or if you wanted, it need not.
Rohan Saxena, Manav Kakar, Aryamala Shivakumar all ask, can we really consider AI art unique or creative? Could a machine write stories or make original poetry using AI? How could it merge emotional sentiment like that? What model would a machine use to achieve that?
Okay. So there are multiple, this is a hyper question, similar to a hyperparameter in some sense. Let me try and answer some pieces. Machines have in fact written novels, right? And this generative model that I just discussed, some more sophisticated version of it was in fact used to write a novel. I can also say that the novel produced by one particular machine actually made it through critics, through a jury, through a judging process, into a set of finalists. Right? So it wrote a novel that was believable enough, that as if it was actually written by an author. Now, the other thing, and I don't want to sort of take this leap, but in some sense, emotion produces output of certain characteristics. So if I could, for example, collect all paintings that were generated under a certain or in a certain emotional state, perhaps training the machine would result in outputs that had elements of that emotional state. And that is why the poll, which was a lookup table. So you might say, well, a lookup table is something that is is something that has happened. But if you think that in the limit, a lookup table could give you the impression of creativity, because it could come up with unique answers, and you could even, give an output which is a negotiation between several different elements of the, or several different entries of the lookup table. So it could be something which has elements of multiple things that happened, but is not identifiable with a specific thing that happened. So I would not make it these are obviously great human qualities, and we are very, very far from replicating any one of them, if they are at all replicable. But to some extent, we could mimic some of these characteristics. And the extent to which we can mimic is getting fairly sophisticated. Ritu?
Very interesting. Last question is from Biswajit Roy. Can we have languages as an input to the encoder? And if so, can we derive semantics of the generated language?
Yes, you can. In fact, if you use Google's machine translation, so you can enter it. If you've not used it in Google, you can go and you can, in the machine translation module, you can enter a sentence in English and you might get an output in French or whatever you select. That machine translation actually relies on a machine, on a neural network. So you could have very complex linguistic rules, but the machine generated translation actually is more competitive, is better than the one achieved through conventional methods. So yes, you could very much do that.
Okay. Unfortunately, we're out of time. So many questions, so little time. But thank you so much for tonight's discussion. I think we're all really illuminated, and we feel like we can all build the next, like miracle drugs and the next self-computing, self-driving cars. I hope our audience enjoyed this session. You'll be surprised to know we had over 150 participants and over 200 questions. So thank you so much, Professor Kotari.
Thank you, Rutu. It was a pleasure, and thank you, everyone. Keep safe, please.
Okay, thank you so much again for everyone for sticking around for the talk. Now we're gonna have a quiz, and remember that the top 5 winners are gonna get exciting prize hampers. So we have a link on the chat feature to the quiz. So click on that, and the quiz will close 2 minutes after the seminar closes. Some of these questions are really interesting. Wow. There's so many questions on the justice system and artificial intelligence. It's really surprising how many places it can be applied to. In fact, that's one of the reasons I was even interested in computer science.
Wow. That's really exciting. I think the art of the possible is yet to be defined.
Yeah. I hope everyone's enjoying the quiz. I mean, some of the quiz questions even I couldn't compute, like the tic-tac-toe example. There's so many big numbers. I can see why the modern AI computing is much more efficient and faster than the classical approach.
Indeed.
I think there's a lot of interesting perspectives in on creativity and computer science, though. It was a really interesting talk. But anyways, we are finishing the quiz now. And so I hope that everyone enjoyed the quiz, and good luck to the winners, whoever you are. The winners will be announced tomorrow, the top 5 on Ashoka's website, ashoka.edu.in. So check it out. On behalf of Ashoka, I'd like to thank all our participants and the audience for joining us today and giving us your time. This was the 4th lecture of Scientifically Speaking. I hope you enjoyed it. And on behalf of Ashoka University and our team, I hope that you all stay safe. We'd also really appreciate your feedback on this seminar. It's just going to take 30 seconds, and it's a survey that's going to pop up when you close this. So do let us know, because it's going to help us improve for the next seminar. Follow Ashoka on Instagram and FB for updates on the next lecture. Thank you once again for your time. Have a great week. Stay safe, take care, and see you next Tuesday for another episode of Scientifically Speaking.